What is an ideal fluid? Well, for a fluid to be an ideal fluid, it needs to have three properties. The first one being laminar flow. Okay? Laminar flow means that it is streamline. Okay? It means the particles are predictable. So if this particle is in the lead, then this particle is going to follow straight behind it. Okay? They follow straight behind each other. You know exactly what the next particle is going to do. Okay? Second thing, it needs to be incompressible. Now, in reality, fluids are a little bit compressible, but it needs to be as close to incompressible as possible. It needs to be pretty much incompressible. So you cannot just push on it and make the volume smaller. Okay, it can't be compressed. And the third thing it needs to have is low viscosity. Okay, that is like the thickness of the fluid. So it needs to be not so thick, okay? And in reality, what it does is when it's thick, there's a lot of resistance and there's a lot of internal friction, okay? We want low internal friction, okay? An example of a fluid that has low viscosity would be like water. An example of a fluid that has high viscosity would be like molasses, okay, or syrup or honey, okay? Those have high viscosity. For an ideal fluid, we need to have a low viscosity. It needs to be incompressible, and it needs to have laminar flow. Okay, once we have an ideal fluid, what can we do with it? Well, we can look at this next situation, which is going to lead to our continuity equation. Okay, so this is a pipe, okay, and you've got a certain volume of water that's come into this cross-sectional area 1, okay, and it's going to flow through, and then this pipe gets smaller. Okay, the diameter of the pipe decreases, but we still have this fluid in there. Okay, so because this fluid is incompressible, the volume of fluid here in section 1 is the same as the volume of the fluid in section 2. Okay, it's spread out more here. Okay, but the volumes are the same. Okay, now I'm going to go ahead and in any equation, if we do the same thing to both sides, we're allowed. Okay, it remains equal. So I'm going to divide both sides by the time. Okay, and then I'm going to go ahead and look at what volume is. Well, this shape up here, I have a cylinder, okay, for this shape. And that means that I'm going to take the cross-sectional area and multiply that by the height, or the length in this case. So the volume 1 is equal to the cross-sectional area 1 times the length, or the height, of 1. I'm going to substitute that in where the volume needs to be. So the cross-sectional area times the length, and then I still have that over the change in time. Similarly, this is a cylindrical shape as well, so to find its volume, you have the cross-sectional area 2, okay, and then times the length of 2. So I've got cross-sectional area 2 times length 2, and I'm still going to have that divided by the time. Okay, now, when I look at this equation, we've had a distance divided by a time before. We call that its speed. So area 1 times the speed at which the fluid is moving through there is equal to cross-sectional area 2 times the speed at which the fluid is moving through that section. Okay, so what's going to happen here, okay, these are the same. Notice the cross-sectional area from 1 to 2 in our picture got smaller. So this went down. If these two quantities are equal, that means the volume, or the speed at which the water is going through there, needs to increase. Okay? You've experienced this before. Let's say you want to go wash your car, but the nozzle isn't working on the end. Okay? So you just go ahead and take your hose, and when you want the water to come out faster, you stick your thumb over part of it. You make the cross-sectional area smaller, and now the water sprays out faster. It's the same amount of water spraying out, it's just coming out faster. If you stuck that into a bucket, it would fill the bucket the same rate whether you put your thumb over it or not. Okay, the volume of the water coming out is still the same, but if you decrease the cross-sectional area, it needs to come out faster so that volume can get out as to what it did before. Okay, now we call this the cross-sectional area times the speed. We call that the flow rate. Okay? Sometimes we write that also as the volume divided by the time. That is also the flow rate. Okay? This is the flow rate. Okay? Again, we took this equation, turned it into that one. Okay? Pretty simple. All right, so now let's go ahead and take this and look at Bernoulli's principle, because Bernoulli's principle also talks about ideal fluids, and it says that as the speed, conceptually, Bernoulli's principle says, as the speed of a fluid increases, the pressure within the fluid decreases. All right, so what does this mean? Well, air is a fluid, okay? There's a tornado outside. The wind is picked up. It's going really fast, okay? So the speed of the air has increased. That means the pressure outside has just decreased. And what happens is high pressure moves towards low pressure. So that's why in a tornado, the windows might actually blow out, okay? Because the pressure outside has decreased, and then the pressure inside is high, and the high pressure moves to the low pressure. Okay? Another example, you've got your lawnmower, okay? Its blades moving around pretty fast, okay? So the air is moving pretty fast inside there. So the pressure has decreased right here, and that sucks the trimmings up, and then they get shot out the side. Okay? So this is the conceptual idea. Mathematically, it's a little bit of a long equation. Okay? What it says is pressure 1 plus 1/2 rho times the speed 1 squared plus the density times gravitational field times the depth 1 is equal to the same thing at a second spot. So pressure 2 plus 1/2 the density times the speed at the second location squared plus the density times the gravitational field constant times depth 2. Okay, so this is the mathematical version, but conceptually it's back up top.